Greetings, fellow Earthlings. Welcome to my video about Newton's 3 laws of motion. Let's begin by taking a look at these two eggs, and I'm going to tell you that one of them is raw and the other one is boiled. I'm going to spin them and try to stop them with my finger, and I want you to figure out which one is boiled and which one is raw. This is egg A. Egg B seems to have a little bit of resistance with me trying to get it to spin. And when I try to stop it with my finger, just from looking at it on the outside, it appears to start moving again. I want you to think about why this is, and before I reveal the answer, let's talk about Newton's first law. Law number 1, also known as the law of inertia, states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside unbalanced force. Now that we know this, the correct answer is that egg B is raw. This is because it's still fluid inside, and when I try to spin it, the yolk inside wants to stay at rest, and when I actually get it to spin, it wants to stay in motion. This also reminds me of the time my brother's sled hit a bump on the hill. The outside unbalanced force caused the sled to slow down quickly, whereas his body wanted to maintain its state of motion. 5 years later, and he still thinks he can defy the laws of physics. A very important word to understand is inertia, and I like to define it as the tendency of an object to keep doing what it's doing unless it's given a good reason not to. And remember that inertia is synonymous with mass. Ronnie. Yeah, get it. Ronnie is a big dog, and he has a lot of mass. This also means he has a lot of inertia, and although he can run very fast in a straight line, the large amount of inertia makes it difficult for him to change directions quickly. Because of inertia, the quarter stayed at rest, even though an outside unbalanced force caused the card to slide out from under it. Now for law number 2. The big equation is force equals mass times acceleration, where force and acceleration are directly proportional, and mass and acceleration are inversely proportional. Now let's see this in action. So the mass of the ball will stay constant, it's not going to change, and I could kick the ball with a little bit of force, not get a whole lot of acceleration, or I could kick the ball with a lot of force and get a lot of acceleration. Ow! But what if we keep force constant and change the mass? This one has a bag of sand in it, and this one is empty, and let's see what happens to the acceleration. The one with less mass has more acceleration. Have you ever noticed that when you take a helium balloon in the car and start to accelerate, it actually leans in the opposite direction you would expect? We all know what happens to a cup of hot coffee when the car speeds up or slows down too quickly. Think about Newton number 1. But why is it that the balloon does the opposite? Well, first we have to know why it floats. I should also tell you that I filled the balloon with hydrogen, which shouldn't really matter too much since it's also pushed upwards, or I should say away from Earth, just like helium, as long as the mass of the gases inside the balloon, plus the balloon material itself, is less than the mass of the gases it displaces in the air around it. When the car accelerates forwards from rest, the air wants to stay at rest, so the gas becomes more concentrated towards the back of the car. This means that the net force on the balloon due to collisions with the air will be in the forwards direction. In other words, the buoyancy force that was once pushing the balloon vertically upwards is now pushing at an angle towards the front of the car. This doesn't just work when the car goes from rest to moving or moving to rest. The key is acceleration. The balloon will lean in the same direction as the acceleration of the car. If there's no acceleration, there's no net force, meaning that the forces are balanced and the balloon will remain or return to its upright position. Another way to demonstrate this is with a cork in a bottle of water. It's even easier to just watch the bubble of air. You could run forwards, backwards, or spin in a circle. Last but not least, Newton number 3. For every action, there is an equal and opposite reaction. Jorgen pushes on the wall, and the wall pushes back on him with an equal and opposite force. So when you drive a car, the car pushes back on the earth, and the earth pushes the car forwards with equal and opposite force. And if you don't believe me, then check this out. Stay. And there you have it. We can clearly see that the car does push back on the paper as it tries to go forwards, but it doesn't really go anywhere because of the pencils and the small mass of the paper. With a real car, we don't notice the acceleration of the Earth because it's infinitesimal compared to the acceleration of the car. This is because the Earth has a much greater mass. And if you don't believe me, then check this out.